Oh, right. Okay, I think now we are live. So, yeah. Hello, everyone. So, today we're going to learn about catalysis. And this is our book, Fundamental Concepts. So, this is our book, Fundamental Concepts in Heterogeneous Catalysis. It's written by like the four giants in catalysis: Jens Noskov, Felix Studt, Frank Bild Peterson, and Thomas Bidegard. They are like the really big names in catalysis. All right. So how do we do this? So first we need to read, like skim the book, and we need to like pick up some important ideas and important assumptions. Then we need to put them in here. So in this mind map, and so the title of this is the theory of catalysis, which I'm going to like lay out all the important points that I think should be considered if you are doing like computational catalysis research. All right. Fundamentals. Okay, so yeah. All right. So from the theory of catalysis, we can see that. So from a broader point of view, we have like two things. One is called thermodynamics, and one is called kinetics. So we have like two things. One is called the thermodynamics, and the other one is called kinetics. Okay. So thermodynamics is dealing with like the energy, the stability, and also like the general properties of the catalytic system. And kinetics is mainly talking about the like the rate of the reaction and the actual reaction pathways and the activation energy, those kind of things. All right, so yeah, so I think the first chapter is, oh sorry, so I think the first chapter is like all about the importance of heterogeneous catalysis. I think if you are reading into this topic, you don't need the motivation. So let's go to the really important stuff. So for the thermodynamics, and I think we need a system. Because for thermodynamics, the most important is the system. And for catalysis, we are looking for catalytic system. So what does a catalytic system have? It has a surface and it has absorbents. That's it. So we have a surface, we have absorbents, also maybe we have the reaction. Yeah, because we want to study like a reaction on a surface, right? So we want to do that. And the adsorbates, for the adsorbates, you can, so surface reactions, yeah, so you can say adsorption, surface reactions, diffusion. Diffusion is important. For adsorbates, we have absorption, we have diffusion, because adsorbates can like diffuse on the surface. And we also have this adsorbate interaction. And structure dependence, maybe it's correlated with the surface, because for surface you can have geometry. So you can have different geometry, like Miller index of the surface. And also you have the quantum and thermal corrections to the ground state potential energy. All right, so you have a catalytic system, right? Now you have a system. The most important thing in like thermodynamics is the energy. So there are like different kinds of energies. So I think the most important one is free energy, or let's call there is either Helmholtz free energy or Gibbs free energy. So Gibbs free energy is at the constant temperature and pressure, but Helmholtz energy is at constant volume and constant temperature. So this is the difference. So for the energy, we have the free energy, and free energy consists two things: the entropy and the entropy. But the energy also we have the corrections. In here we can see there are like quantum correction and thermal correction. I'm not sure what this means, but like we'll get them later, because now we are just building this kind knowledge of trees, and we need to put like everything that is important in there. All right, so let's say surface equilibria. Surface equilibria. Energy. So surface equilibria. Chemical equilibria in gases, solids. Surface equilibria basically means that the surface phase diagram. Is that so? Surface equilibria, which can lead to the coverage of absorbates and the surface phase diagram. The surface phase diagram. So there is one specific of the surface forbade the free energies reaction. So energy, this is for system. For reaction, actually this is the free energy diagrams. So the free energy diagrams is important because it can give you like some important information, like for potential determining steps, what we call PDS. And you can, so there are free energy diagrams, and you have over potential, and you can have potential determining step. So this is the surface equilibrium. All right, now let's move on to the kinetics. So for the kinetics, it's usually regarding a reaction. So for each reaction, we need a reaction mechanism. We need a mechanism, and after we get the mechanism, we want to calculate the rate, the overall rate. But the overall rate, okay, let's see. Yeah, so in order to calculate the overall rate, we need the reaction mechanism. So you can see in here that the hierarchy of these trees is not determined. So if in the later stages, I kind of figure out a better way to organize all those concepts, then we will like change the order and also the things in here to make it like better organized in a certain way. And once we have a like a certain research project, we want to study like a mechanism of a reaction on certain surfaces, then we know where to start and what kind of concepts we can use. All right, for the kinetics, we have the overall rate. So for the reaction mechanism, and once we have figured out the reaction mechanism, we'll know what kind of elementary steps. And for each elementary steps, we need the rate of elementary step. And for that, we need the mass law, I think it's called. The mass law. We need the mass law. Oh, sorry. So which means that the rate, so if the mass flow rate K, so A is B. All right. So the mass flow, if we're assuming A plus B is C. Yeah. So the rate is K. K is the rate constant. So if we want to study the rate constants, see the timescale problem in simulating rare events. I think this is correlating with the molecular dynamics simulations. So usually, if we are trying to calculate the rate constant, we can use transition state theory. That means we need transition state theory, and the theory is something like this. KBTH exponential KBT EA. All right, so it's something like this, and EA is what we call activation energy, and this is EA. Yeah, so EA is the activation energy, and this one is the transition state theory. So we can see that from the overall rate, we have the rate of elementary step, and after we have done see, you can here's the transition state theory, and there are also other things, recrossings and variational ST. All right, maybe it's in here. So recrossings and variational transition state theory is like different. Like different than the normal transition state theory. So kinetics, rate constants. Right, and also we have this thing called harmonic transition state theory. So for the kinetics, once we have the rate of elementary step and we have the reaction mechanism, then we have the overall rate. But in order to get the overall rate, okay, once we have that, then there is a thing called microkinetic modeling. Yeah, so the microkinetic modeling basically means that you combine these things. Okay, I don't know. I'm not sure how to this. All right. So basically in here what I mean by is that you combine the reaction mechanism and the rate of elementary steps, then you can get the microkinetic modeling. And once you have that, then you will have the overall rate. Then the overall rate reflects to the kinetics. All right. So here's the energy trends in catalysis. All right, so we're talking about energy again. And this one, there is a most important thing called absorption energy. And for the absorption energy, we have like phase-swapped energy correlations for phase-swapped systems. Phase-swapped chem-swapped. And for chem-swapped system, we have a thing called a scaling relation. And when it write an equation, I like to use alpha beta. Yes, so it's like this. This to be just to be more concise. All right, so we can say that the absorption energy of OOH is the linear relationship between the absorption energies of OH. So the alpha and beta are just linear coefficients. So here's the ChemSorb system. And you have the absorption energy and you have the reaction. Free energy diagrams. Free energy diagrams, which also means that you have the Gibbs free energy of elementary steps. And for the Gibbs free energy of elementary steps, there is a thing called Bronsted-Evans-Polanyi relation. It's what we call BEP relation. And this BEP relation is like this. Sorry, I'm not sure whether this is good. All right, I'm using my Yeti microphone. All right, this is good. And what this Bronsted-Evans-Polanyi relation did is that alpha G plus beta. It's something like this. So what does this mean? This means that the free energy change of the reaction. So the activation energy of these elementary steps is linearly dependent on the free energy of these elementary steps. So if the same reaction on different surfaces, if their free energy is different, then the activation energy is also different. I think this works when the same elementary steps uh, when the same elementary step for the same on different surfaces, there will be different free energies and activation energies. All right. I don't know how to to type math in here, which is which I think should need improvement uh, because you can type like math in here, but sometimes when you're taking notes, you also need to be able to type like math equations in here. But yeah, I can use latex syntax that in there. But if I want to like see what kind of equations I have, then I can open latex and then I can see it. All right, so here's the thermodynamics and the energy trends in catalysis. Now what we have here, we have the activity and selectivity maps. Selectivity maps. So this, so overall rate, not only we have kinetics, so how fast, is that we also have selectivity. So selectivity basically means that you can have multiple reaction channels, so and multiple products, and we want to make sure that one product is what we want. So this is what uh, selective means: variations in the activity maximum with reaction conditions. All right, so this is the microkinetic modeling, and it can get the overall rate. And what it can get is the, I like to call it the rate function. The rate function, which is r equals, so C and temperature, pressures, and yeah, temperature, pressure, yeah, it looks like this. So C is like the concentration of okay, insert a note. C, concentration of all reactants and products, and T means temperature and P means pressure. So if I give you information about the concentration of each reactant, and I give you temperature and I give you pressure, you should be able to calculate the rate. All right, so activity and selectivity maps, we have that. And the electronic factor, all right. I think surface equilibria. Adsorbate interaction should go in here. And energy, electronic factor. Surface equilibria is also energy. Is also energy. So reaction, absorption energy. Absorption energy is above. And these are the basic concepts. And these are like the applications. So you have basic concepts. And energy, this is behind this. We have basic concepts and we also have applications. for the application, we can have the absorption energy and also the surface equilibrium. All right. Now I think it should be like really simple. And this is our system. This is the energy. And for energy, we have basic concepts. For example, the Helmholtz gives free energy, and we have corrections on that. And we have applications. So there are three applications. One is absorption energy, second one is surface equilibrium, and the last one is the reaction. But as for the energy of that, we also need what's called descriptors. All right, so overall rate, and you have selectivities. For the kinetics, you have descriptors. And there are many descriptors like geometric descriptors, electronic structure-based descriptors. So this one is the electronic factor in heterogeneous catalysis. So the descriptor could be used to correlate the absorption energy, and it also could be correlated with the rate of the reaction. So the most important one is the D-band center and the D-band model. So from the D-band center, we know there is something called the ligand effects. Ensemble effects. We know that D-band has ligand effects and ensemble effects. All right, and here are some like specific applications. Oh, geez, how do I get back? How do I go back? Go back. All right. Go back. All right. Catalyst structure, nature of the active site, structure of the real catalysis. Catalysts, intrinsic structure dependence. I think these are all in here. So in the surface geometry and the nature of active site. Intrinsic structure dependence. Nature of the active site. It could be like on surface with support or with structural promoter, like something like the precursor. Yes, some surface precursor. So for example, if I mean like sulfuric acid, there may be some sulfate that is on the surface. Poisonous and promotion of catalysis. Okay, surface electrocatalysis. So this is a very specific system, where the applications surface equilibrium energy is called the surface electrocatalysis. Why this is important? Because catalytic system, because it has something called the electrolyte interface. All double layer called double layer. So this interface is very important because when you change the potential, you can like really change the activity of the reaction. Electron transfer. Electron transfer process. See the potential dependence of the rate. The over potential in here. Here turns the limiting potential map. Yes, so those are all the stuff. So the limiting potential map is just an extension of this, the free energy diagram. So in here, the over potential, what I mean, the over potential is just over potential usually is called eta. The over potential format map. Okay, style format. I need to be like this. Yeah, like this, yes. Oh, good. So I can select all and just doing this. Okay, that's good. Okay, and for this one, all right. So the relation of activities to surface electronic structure. The D-band center is correlated. So the core of D-band theory, like D-band theory, Nielsen's model. Nielsen model is very important because this is like the foundation of all the D-band center and also the D-band stuff, and it has been also been applied into alloy research like recently. So this is a very important aspects. Oh, right. Okay, so basically we have like put the overall. This is not a very thick book. It's only like 200 pages, but yeah, it's really good. It's really compact. Preface. We don't need that. All right. So what we did here is, okay, so let me just put this here, and so chi 80%, no, 50%. All right, good. So now we have the theory of catalysis. We can see that here is the thermodynamics and here is the kinetics. The thermodynamics are dealing with the energy related stuff, and the kinetics is related to like the rate. Now we'll go deeper. So we need to understand each concept means. And we also need to be able to use them in like the real systems. And I think this is also very important. And this is just the theory of catalysis. We can also build a general knowledge of the uh, quantum chemistry, because quantum chemistry is also, it's like the foundation. So all these like quantities, different quantities, can be calculated by the quantum chemistry. So I think maybe tomorrow or later I can make a stream talking about the important things about quantum chemistry, about density functional theory, and a different level of theory that we can get in order to calculate the energy and the electronic structure, electronic structure of the surface. And so electronic structure is also very important because you need to have because all chemical bond is actually sharing the electrons. So the motion of electrons is important, and the motion of electron built on the electronic structure of that material. So we really need to understand the electronic structure. That's why this is important. Okay, so now we have kinetics, we have thermodynamics, and I think it's quite late, so I will end my stream right now. And if you are interested, yeah, you can click the subscribe and click the bell. Then next time if I go live, then you will receive a message. All right, good night everyone. See you next time.